Welcome to the third lecture in our series on quantum mechanics. In today's lecture, we will talk about what I refer to as the central mystery of quantum mechanics. In this lecture, we will see how quantum mechanics differs from classical physics and the world that we experience around us. The lecture follows Feynman's famous Lectures in Physics. So volume 3, chapter 1 of Feynman's lectures contains a series of thought experiments or series of experiments which we will talk about in the first half or the first 3/4 part of this lecture. We will start with an experiment with particles. This will tell us how particles behave. We will then follow it up with an experiment with waves, which will tell us how waves behave and how waves are different from particles. Then we will do an experiment with electrons and see whether they behave like particles or waves or none of them or both of them. We will then do some variations on our experiments and show how deep the mystery is. So Feynman did not talk about the delayed choice experiments, but these experiments further the mystery and show us that no matter what we try, the mystery does not go away. In the end, we will talk about the summary from all these experiments. So when I refer to experiments in this lecture, I mean thought experiments. So we will do a set of thought experiments or imagine some experiments during this lecture. But of course, if one were to do real experiments of the kind that we have described, they will get identical results. And people have done real experiments of the kind that I will describe, and the results are exactly what we expect. The first experiment that we will do is with particles. In all experiments, we have a similar setup. So here we have a gun which fires bullets. Of course, the bullets go in a straight line, but this shoots bullets or it sprays bullets in all directions. At a little distance from this gun, we have this panel. Bullets cannot pass through this panel except at two places. So there are two holes in this panel, hole A and hole B, and bullets can only pass through this panel to either hole A or through hole B. In front of the panel, we have this back panel. Bullets cannot cross this, and any bullet that hits this back sheet or back panel will get absorbed by it. We can place a detector at any place on the back panel. The detector counts bullets, it can accumulate bullets, and this detector can be moved to any place on the y-axis. So we can see how many bullets land at that place. This kind of a setup is called a double slit experiment. So now let's start our experiment. Let's fire up this gun. It starts shooting bullets. The interesting thing that we observe while doing this experiment is that the detector always counts full bullets. It cannot count partial bullets. Or rather, this detector will always count a whole number of bullets. And this is what common sense also tells us. So bullets behave like particles, and particles come in chunks. Either a particle comes or a particle does not come. It can only be a whole number of particles. So the first part of this experiment involves closing hole B. So you close hole B by putting a barrier in front of it. So the only bullets that can pass through are through hole A. So bullets go through hole A and they bounce off and they go to different parts of the back screen, and there they are detected. So after all the detections are done, we can see which part of the back screen received how many bullets. Of course, our detector will have to be moved to different places to count how many bullets were detected at that part of the back screen. What we observe is some kind of a pattern like this. This shows the number of bullets detected at different parts of the back screen when only hole A is open. As we can see, most of the bullets are detected in front of hole A. This figure that I have drawn of number of bullets is not very accurate, but basically the point is that most of the bullets are detected near hole A and very few are detected near hole B. A bullet can be detected at any place because it might bounce off A and reach that point, but most of the bullets are close to hole A. Now we remove the barrier in front of hole B and we put a barrier in front of hole A. So we stop the bullets coming from hole A, and now the only bullets are coming from hole B. So once we have completed our experiments and accumulated all the bullets at different places, the curve will look something like this. So it's a similar curve to what we had observed earlier, except that now it peaks at hole B. So most of the detection now is close to hole B. So the first curve we can name BA, and the second curve we can call it BB. So basically what we are measuring here is the probability of a bullet being detected at a particular place on the back screen. And so this probability of A is the probability of detection when only hole A is open, and probability of B, the distribution, is where we expect more bullets to be when only hole B is open. Another way of looking at it is there's an intensity of A and an intensity when only hole B is open. So by intensity we can define as number of bullets per second. So this curve can equally be interpreted as two intensity curves. Now let's remove the barrier in front of hole A as well. And now let's do an experiment in which both holes A and B are open. When both holes A and B are open, the curve that we see looks something like this. So this curve is now peaked in the middle of two holes. So most of the detection is right in the middle of the two holes. Let's express this mathematically. If we do the calculations right, and if my curves were more accurate than what I have drawn them, then probability when both A and B are open at any particular place on the back screen would be probability of detection at that place when only A is open plus probability of detection at that place when only hole B is open. In other words, intensity AB equal to intensity when only A is open plus intensity when only B is open. So this kind of tells us how particles behave. To summarize, particles are detected in chunks, that is, can only be whole numbers. In other words, particles are quantized. And second thing is that the intensity curves or the probability distribution curves add up. So to find the probability at any particular place when both holes are open, you can add the probabilities when hole A is open to the probability when hole B is open for detection at that particular place. Now let's do an experiment with waves. The setup is essentially similar what we did with particles. However, there are some differences here. Instead of the gun which shoots bullets, we have some kind of a wave generator which creates waves. So you could do this experiment in air or in water. So if you were to do this experiment in water, you would have something which creates waves in water. Also, this detector is now a wave detector. So instead of counting bullets, it measures the height of the wave that it encounters. In the last experiment, we defined intensity as the number of bullets per second. So that is essentially the energy carried or the energy received by the detector per second. Here also, we can define the intensity in a similar way, which is energy that the detector sees per second or per time. Now, in the case of waves, so detector is measuring the height of the wave, and what we find is that the energy is basically proportional to the square of the height. So we write intensity equal to height squared. So again, this is our hole A and this is our hole B. Now let's start this experiment. So this generator creates these waves, and these waves strike hole A or hole B, and from this these new wave fronts are created, or these new waves are created, and so on. Again, similar to what we did in the previous experiments, if we close hole A and only detect the waves coming from hole B, we will get a pattern like this, which essentially means that if hole A is closed, then most of the detection is at hole B. So that means our detector, which can be placed in front of B, will see a lot of wave activity, or will be able to detect a lot of incoming waves. And the detector, if placed in front of hole A, will not see much action. Similarly, if hole B is closed, then what we see is that, as we expect, most of the action is around hole A and very little is around hole B. So a detector will see a lot of up and down motion near A but not much near B. One important comment we must make here is that in the case of bullets, our detector always detected a whole number of bullets. So it could detect 10 bullets or 11 or 12, but never 10.5. But that constraint does not exist in the case of waves. So a detector can detect waves of 1 meter or 1.2 meters or even 1.25 meters. So there is no restriction. There is no lumpiness about waves. They can come in any size and waves are not quantized. Now let's open both the holes. When we open both the holes, the pattern that we see will look like this. Something of this sort. Now this is very different from the pattern that we observed with particles or with bullets. What this essentially means is that there are some places where almost no wave activity or almost no energy is detected. And there's some places like this one where you can detect a lot of energy. So if you were to plot this as intensity, then you can see a lot of intensity here, but almost zero intensity here when both the holes are open. Now this pattern is very different from the pattern that we saw with bullets. What this means is that intensity of detection at any particular place when both holes are open is not equal to intensity when only hole A was open plus intensity when hole B was open. So intensity AB equal to intensity A plus intensity B in the case of bullets, but it is not equal to intensity A plus intensity B when in the case of waves. What we see here is called interference. So at some places like this, the two waves cancel out each other. And some places like this or this, the waves add up to create a larger intensity. So waves exhibit interference and do not add up like particles. So this gives us the formula for the intensity when both A and B are open. So it is not just IA plus IB, but there's this extra term. This is the interference term, which basically can reduce or increase the IA plus IB. So this delta here is the phase difference between the two waves as detected at that point. So summarizing, waves are different from particles in two ways. One is that waves are not quantized like particles. Our detector can detect waves of any height. And the second thing we notice is that the intensities do not add up simply, but they add up according to this formula. And at some places, the waves destructively interfere with each other, and at some places, constructively interfere with each other. And that causes, or that gives us a pattern like this, which is called the interference pattern. So we have done our experiments with particles and with waves. Let's now do the same experiment, but with electrons. We want to understand how electrons behave and whether they behave like particles or like waves. The setup is similar. On the left hand side, we have an electron gun. The design of this can be simple. We could have a tungsten filament which is heated, and electrons will come out of that, and using a positively charged plate, we can accelerate them towards our two slits. So we have this two slit setup with slits A and B, and on the back screen we have a detector. Now the detector can be a Geiger counter. This basically makes a clicking sound whenever an electron is detected, and this detector can be taken to different parts of the back screen to see how many electrons reach that part of the back screen. When we do this experiment, the first thing we notice is that our detector always records clicks of the same loudness. So whenever the detector detects an electron, it clicks, and all clicks sound the same. This suggests that electrons, like bullets or like particles, are quantized. That is, either you detect an electron or you don't detect an electron. There's no half electron or 1.2 electron to be detected. So electrons seem from this observation to be quantized or behaving like particles. Let's now start our experiment. As we did earlier, we first close hole B, and when we close hole B, we see a pattern which is similar to the pattern we saw earlier, that most of the detection is near hole A. So this is number of electrons. So this is our probability distribution when only hole A is open. Let's now open hole B and close hole A. With this, we get an expected result. So most of the detection now is in front of hole B. So we call this PB. Let's now open both the holes and see what happens. Will it behave like particles, or will we get a wave-like behavior? Since our detector is always counting full clicks, our assumption is that electrons should behave like bullets or like particles. But let's see what we actually get. So what we get is pattern like this. So we get an interference pattern very similar to what we got in the case of waves. Now this is strange because our electrons were behaving like particles and we always saw whole number of clicks or a whole number of detections in our Geiger counter. But this interference pattern suggests that the electrons are interfering with something. So let's make a change to our electron gun. Let's decrease the temperature of our tungsten filament. What happens now is that our detector will click less number of times, but the loudness of each click will still be the same. What this means is that the number of electrons coming out of the gun has decreased, but each electron is still giving the same loudness in terms of clicks. This suits us because this will now let us decrease the temperature such that we hear clicks sufficiently spaced. So we decrease the temperature so that the clicks come after a large interval. What we are doing effectively here is passing electrons only one by one through either hole A or hole B, because once they reach the back screen, there's only one click at a time. So either the electron is going through A or going through B. And we never have a scenario in which there are two electrons at the same time. After we have done this experiment long enough and we have passed enough electrons through our double slit screen, we still see the same interference pattern. So even though we were passing one electron at a time through the double slits, still it managed to create an interference pattern. Now this is very strange because in the case of waves, we can understand the waves coming out of A interfere with waves coming out of B, but here we have electrons which are coming one by one. What are they interfering with? Is one electron passing through both holes and interfering with itself? So this is what is very strange about quantum mechanics. So our electrons seem to behave like a mix of wave and particle. In terms of detection, in terms of clicks in our detector, it seems to behave like particles and it seems to be quantized. But in terms of the pattern of observation at back screen, we see an interference pattern, and that seems to suggest wave-like behavior. So this red curve is PAB, and as in the case of waves, PAB is not equal to PA plus PB. In the case of waves, the intensity was proportional to height squared. So the detected height at any given place, the square of that height of that wave was the intensity. Intensity when both A and B were open was something of this sort. So we have seen this expression earlier, and we said that this is the interference term, and IAB is not equal to just IA plus IB, but there's an extra interference term which causes the intensity at some places to become zero and at some other places become very large. So this was what we saw in the case of waves. What we see here in the case of electrons is something of this sort. So instead of height, we have this complex function known as the wave function, and we will talk about that in subsequent lectures. But the probability of detection when both holes A and B are open is not PA plus PB. It is in fact the square of the sum of two complex functions, and this will lead to some kind of an interference term of the kind we observed here. So to summarize, electrons are behaving in a very strange manner. They show some characteristics of particles and some characteristics of waves. They are quantized like particles, but they produce an interference pattern like waves. And even if we send one electron at a time through the double slits, we still get an interference pattern, which is very strange because we don't know what the electron was interfering with. How do we resolve this mystery? We do not understand how our electron can seemingly interfere with itself and create that interference pattern. It seems that the electron is up to some tricks. In order to resolve this, let's do a variation of our previous experiment. This experiment has the same setup as earlier. The only difference is that just after the two holes, that is hole A and hole B, we place a light source. So again, this is our electron gun. Our assumption is that when the electron is passing through, say, hole A, light will strike that electron and we will see a little flash somewhere around here. Similarly, we will see a flash near hole B when the electron is passing through B. So we will be able to find out which electron is going through hole A and which electron is going through hole B, and how the electrons can interfere with themselves. So this is again our detector, and we can move the detector to different parts of the back screen. We fire up this experiment. Whenever we see a flash near hole A, we add the count to one list along with the position where it finally ended up. And whenever we see a flash near hole B, we put that count in another list along with the position where that electron was finally detected. So now let's plot the detected electrons which are seemingly coming from hole A. We will see a pattern of this kind. So whenever there's a flash near hole A, we plot the probability density at different places or number of electrons detected at different places on the back screen, and it looks something like this. This is similar to the pattern that we observed when we had closed hole B. So it seems reasonable. Similarly, whenever we see a flash near hole B, let's plot where those electrons finally ended up, and we will see a pattern which is like this, which is again similar to the pattern we got earlier when hole A was closed and only hole B was open. But what about the total pattern? That is not just hole A and hole B, but the total detections on the back screen. Now, since we are counting the detections when the electron is passing through hole A separately, and we're counting the detections of electrons that pass through hole B separately, all we need to do is to add them up to get the total detection at different places. And by definition, the probabilities have to add up, or the number of electrons have to add up. There is no way we can produce an interference pattern by doing something like this. So the pattern that we will see would of course look something like this. So this is our back screen and this is our probability pattern. I'm not drawing this pattern in this area because I would need to draw similar patterns a few times and this place will get cluttered. But the basic idea is the two probabilities will add up and it will create a pattern which is the sum of probability A and probability B. This is exactly what we saw in the case of bullets. So something strange has happened. We were able to detect which hole our electron passed through and we could trace whether it passed through hole A or hole B, but we lost our interference pattern. So this is strange. Instead of solving our mystery, this has deepened our mystery. It seems that our light source is causing some complication to the trajectory of the electrons and changing their paths and not allowing them to interfere with each other or with themselves. So let's reduce the intensity of the light source, reduce the brightness or the intensity of the light source. Our assumption is that maybe the electrons will not get as disturbed with a less bright light source. Now something interesting happens. Some of the electrons pass through A and are detected by this little flash here. Some of the particles pass through B and are detected by a little flash somewhere around here. But some electrons are not detected by these flashes at all, but instead are detected only when they hit the back screen. So we are missing some electrons. And this is because when we reduce the brightness, we are effectively sending less photons from our light source. Sometimes when the electron is passing through A, there is a photon which hits it. But sometimes the photon is just not there. So the electron passes through without hitting a photon and without creating that light flash. So now what happens? For all electrons that pass through A and are detected with this light flash, the pattern looks exactly like this. And for all electrons that are detected near B through this light flash, pattern looks exactly like this. And if you were to add both those sets of electrons, the pattern would exactly look like this. But the undetected electrons or the electrons which did not create a flash create an interference pattern on the back screen, something of this sort. So this is the interference pattern. And this is of course our back screen. So all the electrons that were detected by this light flash and we could know which hole they passed through created this pattern, which is particle-like pattern. And the electrons that passed through undetected and we do not know which hole they passed through created this interference pattern, which is what waves do. Now this is very strange because it seems that whether we detect which hole the electron passes through or not creates either this particle-like pattern or this wave-like pattern. It seemed that our experiment of reducing the intensity or brightness of light did not create the desired effect. So let's try a variation there. Let's reduce the frequency of light of this light source. This is because we know that the energy is proportional to the frequency. So we need a less energetic light source. We need less energetic photons which do not disturb the trajectory of the electrons. We also know that when the frequency decreases, the wavelength increases. So let's make the light source of a lesser frequency. Of course, the side effect is that the wavelength of the light will increase. Now what happens is that every once in a while, we see a big flash. And the flash is so big that it happens in the whole area between the two holes. We see the flash when the electron passes through the holes, but the flash is so blurred and so large that we cannot determine which hole the electron has passed through. The flash is completely non-localized. And after we send enough electrons in that manner, what we see in our back screen is again the interference pattern. So Our experiment in which we reduced the frequency did not work because it did not give us the hole that the electron passes through. So it created that interference pattern. So this is very strange. To summarize, if you know the hole through which the electron passes through, you get particle-like behavior and no interference pattern. In this case, PAB equal to PA plus PB. But if you do not know the hole that the electron uses to pass through, then you get wave-like behavior and you get interference. And therefore, in this case, PAB is not equal to PA plus PB. There is an additional interference term that we studied earlier. The mystery, instead of being solved, has become deeper. It seems that you cannot determine the hole through which the electron passed and still create an interference pattern. So our assumption that the electron was somehow interfering with itself cannot be tested because we do not know which hole it passes through or whether it passes through one hole or both holes without destroying the interference pattern. So let's come to another interesting topic. John Wheeler came up with a variation of the experiment that we have just done to try and further probe this mystery. So this is what the setup looks like. Instead of an electron gun, we have a photon gun. It doesn't matter because all elementary particles show the behavior that we have described in our earlier experiments. So this is our photon gun and it shoots photons just as our earlier electron gun did. And it passes through these two slits, A and B, and there's a back screen there. And this was what our earlier experiment looked like. But now we have two additions. So we have this telescope T1 and telescope T2. Now the experimenter or the scientist has two choices. First choice is that he can let this back screen remain, in which case we should expect to see an interference pattern, which we had observed earlier in the case of electrons. Or the scientist can remove this back screen and then T1 will be focused on hole A and T2 will focus on hole B. In this case, T1 will observe any photon coming out of hole A and T2 will observe any photon coming out of hole B. In this case, every photon should either go to T1 or to T2. T1 and T2 should never see the same photon, which basically is particle-like properties or bullet-like properties. Our expectation in general is that either a photon goes through hole A or hole B, or photon can go through both A and B, thus creating an interference pattern. If it goes through either hole A or hole B, it can never produce an interference pattern, or that is what our traditional classical thinking tells us. So it is up to the experimentalist to choose whether he or she wants to see wave-like properties by placing this screen or particle-like properties by placing these two telescopes. However, the interesting thing is that this choice can be made after the photon has left the slits. The photon leaves the slits and after that we can make this choice. So it is delayed choice. So the photon does not know whether it has to pass through slit A or B or through both, because it has already passed through the slits and after that we are making a choice. And the interesting thing is that when Wheeler proposed the delayed choice, he was thinking about a huge distance between this, the double slit and the back slit and the telescope. So this can even be light years. This can be a huge distance, thousands of kilometers or millions of kilometers or even light years apart. He was thinking about this experiment on an astronomical scale. So variations of this experiment have been tried, though not at the astronomical scale, and each one of them have shown that the predictions of quantum mechanics hold true. That is, when you check the particle nature using T1 and T2, you will get a particle nature, and when you have this back screen there, you will see wave nature, but you will never see both at the same time. So our ignorance about which hole the particles pass through, whether they pass through one hole or through both holes, continues to remain a mystery. Now we have done our experiment with electrons and we have shown that they also show wave-like properties. But in our previous lecture, we said that every particle should have wave-like properties. In fact, de Broglie showed that every particle should have this wavelength. And with the case of electron, we saw that it shows wave-like properties or particle-like properties depending on the experiment that we do. But what about bullets? Our bullets were shown to behave like particles. Do they not exhibit a wave-like nature? So let's do the same experiment with bullets, but now zoomed in. So again, you have this gun and it fires bullets, and you see a pattern of this kind, which tells you that we are dealing with particle nature. But now that we're going to do this experiment zoomed in, let's zoom in into this pattern. And what we find is, indeed, there's a very fine interference pattern somewhere inside this. So when we thought we were observing particle-like behavior, it was actually the wave-like behavior, but it was smeared out and it looked like this pattern, where actually inside it is this pattern. So what we see here is that even bullets will show the same behavior as electrons, but when you zoom into their pattern, you will see that it is made up of a very fine interference pattern. And this is because the wavelength of bullets is extremely small. So where does all this lead us? In summary, in quantum mechanics, there is something called a complementarity principle. That is, objects have certain pairs of complementary properties which cannot all be observed or measured simultaneously. Now, what are these complementary properties? For example, wave/particle. Either you can observe wave-like behavior or particle-like behavior depending on your experiment, but never both at the same time. So these wave and particle nature are complementary properties. Other examples of complementary properties are position and momentum. Other example is energy and time. And we will see more of these. And Heisenberg's uncertainty principle applies to complementary variables. So Heisenberg is telling us that there is a limit to how accurately we can measure complementary variables at the same time. So if you measure the wave property, particle nature no longer shows up. Or if you measure the particle nature of a phenomena, the wave nature no longer shows up. These are limits on the accuracy of our simultaneous measurements on pairs of complementary variables. Similarly, you cannot measure the position and momentum of objects at the same time. And there seems to be no way out of this mystery. In a certain sense, Heisenberg's uncertainty principle and the principle of complementarity keep certain aspects of reality hidden from us. We do not know what is happening inside. We can only measure through experiments. And experimental accuracy has certain bounds. Another thing that comes up is that the observer is key in quantum mechanics. The observer chooses to reveal a certain kind of reality. For example, in our earlier experiments, it is the scientist or the experimentalist who chose to reveal either wave-like properties or particle-like properties. And this causes great philosophical discussion or confusion, because this is the first time in physics that the role of the observer has become prominent. The observer is not merely observing a phenomena that is independent of his or her existence. The observer, in fact, is creating the observation. The observer is responsible for choosing what will be revealed. People like Einstein had great difficulty with this concept because they believed that reality of the universe should be independent of the observer. The reality should be an objective reality and not dependent on the observer. And this led to many debates between people like Einstein and other scientists who chose to go with what quantum mechanics had showed them. We will talk about these aspects in our later lectures. In our next lecture, we will start talking about the mathematical foundations of quantum mechanics. Thank you.